What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we dealt with our very first capacitor lab. Again, capacitors, they look like this. They are part of simple circuits. They store charge. But today, we wanted to figure out what are some things that affect the capacitance or affect the capacitor. What can a capacitor do when it's in a circuit? So we had a simulation that we used. We could have built this in class, but it's hard to take those measurements in class. So instead, we had a simulation. We used a simulation and built a circuit basically like this. We had a battery connected to this parallel plate capacitor right here. And we were able to vary the voltage over here, and then we measured the charge over here. So if you got no data, you didn't take any data, there's some data for you. All right? Go ahead and use that data. Graph that data using Desmos or whatever graphing app you like to use. Use that, okay? That was that. So our plan was to figure out the effect of voltage of the battery on charge stored on the capacitor. So if I could change my battery, how does that affect the amount of charge I can store on a capacitor or that will charge on a capacitor? I want to remind you of something, right? Voltage, the battery, has a different name. We call it voltage sometimes when I'm talking about batteries. When we talk about ideal batteries, batteries that have no internal resistance, we call it the electromotive force. And I think that's important. Because what a battery does, what voltage is it is a force that forces charge through the circuit. Now, it's not a charge, it's not a force in terms of it's not a Newton necessarily. It's a predictive value of energy, of flow of charge, of kinetic energy, a potential energy that can become kinetic energy movement. But whatever the voltage is at the battery basically dictates how quickly charge will move through the circuit. Okay, so as that battery pushes charges through, the greater that force is, that electromotive force that pushes charge through, dictates, or does it, that's our question, does it dictate how much charge stores on the capacitor? So let's look at this, all right? We go ahead and we say, as I increase my voltage, I crank this voltage up here on this ideal battery, what happens to charge? Well, apparently, the more voltage I have in the battery, the more electromotive force I have in the battery, the more charge I can store. And that kind of makes some sense. Because remember, this is the positive high potential side of the battery, which means this is going to be the potential high positive side of the capacitor. And at some point, there's not going to be enough space on this capacitor to add more positive charge, right? At some point, these positive charges get so repulsive that things just back up in this battery. Or you can think about it backwards if you're thinking about the movement of electrons. But electrons fill this plate, and eventually things get so repulsive, it gets backed up and charge stops moving. So with a greater voltage or a greater electromotive force or push, with a greater force, I can store more charge on that capacitor as a maximum. At the maximum capacitance, this is what I get. I go ahead and I graph this data to see what's going on here. If I graph this data and I say, hey, I change voltage, I measure charge, I graph this data, and I end up with a line. I say, okay, what is the line? Now, in my simulation, my capacitance was, the capacitor itself was measured at 0.3 picofarads. Pico is teeny tiny, so small. It was tiny picofarads. Now, my voltage is measured in volts. My charge was measured in picocoulombs, super small charge. So I graph picocoulombs, I graph this in voltage, and I end up noticing that my slope of that line is exactly 0.3 picocoulombs per volt, which is a weird unit. So it's picocoulombs per volt. That tells me the amount of charge per voltage stored on the capacitor. And what I guess I find out from this is that it's curiously close to the capacitance. And again, what does a capacitor do? It has the capacity to store charge. Well, how much charge is dictated by the strength of the battery or the electromotive force. So, what I look at now is say, okay, I guess the slope of this must be my capacitance because it's just so similar. That's got to be, and it's related. That's just got to be the conclusion I make. Let's go ahead and generate an equation from this. Well, I've got Q over V equals the capacitance. And then if you go ahead and you look at your equation sheet and you say, hey, is there an equation on my equation sheet that looks something like this? The answer is, Yeah, it looks just like this. The equation for capacitance, one of them, is that capacitance is equal to the total charge on the capacitor or the max charge on the capacitor based on voltage. So there it is. That's my first equation right here. Capacitance equals this. I get that from my graph right here. Graphs, math, and explanation. Well, the explanation is if I crank up the battery, I'm forcing more charge to load on the capacitor. At higher voltages, I get a greater electromotive force to store. There's more charge to be stored on this capacitor. At smaller electromotive forces or smaller voltages, I get less charge to be stored on there before the whole system backs up and I can't load more charge onto that plate. So that's it. I've got my capacitance equation. I've got my graph right here that indicates that. And then I've got my system over here. I want to show you one thing though, because I think this is interesting, right? I want to show you that no matter what, if I change the voltage, I'm not changing the capacitor. At no point in this simulation, in this lab, did I touch the capacitor. I simply measured the voltage at the battery, and then I measured how much charge was stored here. So, hear me out. If I go ahead and I triple my voltage, let's look at my graph. If I triple my voltage that the battery supplies, does that change my capacitance? And the answer is no, right? If I triple my voltage, does that change the capacitance? No, it just means that there's 3 more times the charge stored on that capacitor. Well, if I want 3 more times the charge stored on that capacitor, do I need to change my capacitor? I could, but also I could just triple my voltage. This is a relationship. So what I would say here, if I'm coming up with a proportionality statement, I would be saying that charge on a capacitor is directly related to the voltage across the capacitor, right? Like if you got more voltage across the capacitor, more difference there, you got more charge there. That just kind of makes good sense, right? But it happens to be a linear relationship. There's no square relationship here. It's just if you got more charge, you got the exact same more amount of voltage. That's the first finding from this lab. Now, the next finding from this lab was, I wonder, like we always check, the slope means something. The slope in this case meant capacitance. I wonder what, if the area means anything. So what is the area here? The area here is a triangle, and if I wanted to find the area of this shaded region right here, I would say it's voltage. It's a triangle. I would say the area is equal to 1/2 the base, which is voltage, times total charge. Now, thinking about this, okay, volts times coulomb, 1/2 volts in coulombs. I wonder what this unit is. Well, if I think about this in terms of units, 1/2 has no unit, so I'll get rid of that. When I'm talking about units, I'll say this is a volt is a joule per coulomb, and a charge is in coulombs. So when I look at what the units of my slope end up being, the units of my area, it ends up being joules, which is energy. I wonder what they're talking about. What could they mean, energy? Why would they be talking about energy of a capacitor? Well, capacitors don't necessarily have charges moving through them. Capacitors store things. And what have we been talking about in terms of like potential energy? Potential energy is stored energy that can be used later. Well, folks, that's what a capacitor does. It stores electrical energy to be used later. The area of this graph is simply stored energy. Let's go ahead and check it out. I have my equation sheet. I go check. The potential energy stored in a capacitor is equal to 1/2 the voltage times the charge. And guess what? That's an equation also on our equation sheet. It's the area of this graph, the voltage over, it's the charge over voltage. There's my area, the integral of that. The area is 1/2 VQ. And then the capacitance is the slope. I can use both the area and the slope in this to determine some things about my capacitor. I want to show you one more thing though, because this is wild. We already said that capacitance doesn't change based on charge or voltage, right? It's an inherent quality of this device. So this capacitance doesn't change unless I change this device. This won't change. So my question is, if I double my voltage, if I take the battery and I crank it from 2 to 4 volts, if I double my voltage, what happens to the stored energy on that plate? So If I think proportional reasoning, I would think to myself, well, initially, I want more potential energy. If I double my voltage, I'll just double my potential energy because I see that voltage is directly related to potential energy. But that's not the full story. That would be assuming the charge stays the same. And for the charge to stay the same when you increase voltage, you'd actually have to change the capacitor. You'd have to make it smaller or different. You'd have to change the capacitor. And we're not going to do that. We're using across the exact same capacitor. If you double the voltage, what happens here? Well, if you double the voltage, you also double the charge. So you're doubling both. So doubling the voltage also doubles the charge. How many times bigger is my stored potential energy? Well, it'd be 4 times bigger. So if I double this, I also know the charge has to double on the capacitor. So double that, 4 times the potential energy. So be careful when you're asked your proportional reasoning questions about this, and don't just go all crazy on me and go, well, it's just look at the one variable. Understand that with the same capacitor, you already know this is the basics. Right? The basics is capacitance is equal to Q over V. That means these two things are directly related. You change voltage, you change charge, you change voltage, unless you change the capacitor itself. All right? We've got 2 equations for capacitance. These are the basics about charge and voltage. If you got questions, obviously, drop me a comment, send me an email, ask me in class. Okay? Until next time. See ya.